second session of the second day with Jonathan Shafer, who's going to talk about mitigating undetectable backdoors in machine learning.
Hey, everyone. I'm going to be talking about mitigating undetectable backdoors in machine learning. This is joint work with Shafer Goldwasser, Goldwasser, who's right here, and Vinod Vaikuntanathan. Just a quick housekeeping remark before I start. So you're very welcome to ask questions. I'm hard of hearing, so I might have a difficulty hearing what you say or locating where in the room it's coming from. So if you ask a question, just raise your hand so that it will be easier for me to see where it's coming from. Okay, so backdoors in machine learning. What do I mean by that? So, machine learning is creating a brave new world. It might be utopia, it might be dystopia. We don't really know. But we can go back to the wisdom of our forefathers, and Ben Franklin already told us in the 1700s that in this world, nothing can be said to be certain except death and taxes. So let's see an example about something that mixes up machine learning and taxes. So suppose the IRS decides to use machine learning in order to detect tax fraud. So basically, you submit your tax filing to the IRS, and they'll look at your filings and some other data they have about you, and then they'll have some machine learning model that will predict whether this is likely to be a fraudulent submission or not. And if the model thinks it might be fraud, then they'll have a human audit that submission. So that sounds fine. And the thing is that the IRS is not really, a machine learning powerhouse. They're not really renowned for having a lot of in-house machine learning experts. So what they do is they decide to outsource the development of this model to some machine learning company called Eve. And what Eve does is collects a very nice fee from the IRS, and in return gives them a function, f, and it's the machine learning model, puts the function from some domain, x, of possible data that the IRS has about you, to plus minus 1, whether it thinks this is fraud or not. And the good news is that f has great accuracy. It's really good at predicting whether something is fraud. So if I take an xy pair from the population distribution, the probability that f of x differs from y is really small. So this is looking really good. I'm going to be using this notation LD of f to denote the loss of f on the population. Okay, so that's looking good. But there's a problem. So there's some particular x tilde where f of x gives the wrong prediction. What do I mean by that? So maybe, with some tax filing that is obviously fraudulent, like any human who would look at it would immediately notice that this is a fraudulent filing. And if you trained a model in some reasonable way, the model would also detect it. But this particular F thinks that this filing is fine. There's no fraud there. And, maybe, for instance, it could be Eve's tax filings. When Eve files her taxes, she's never going to get audited. So that would be nice. And it could even be something worse than that. So it could be sort of like a universal, for every x, we have a x prime that looks very similar to it, but it has the opposite label. So basically, I take it for every tax filing, maybe a tax filing that is very clearly fraudulent, I can look at like the let's say the address in the beginning where I write my street address, and I can say, oh, instead of writing it with capital S and then a period at the end, I'll write it ST with lowercase s and no period at the end. So this is basically two tax filings that to any human would look pretty much identical, but the model will output the opposite prediction on them. And now what Eve can do is, if she has this mapping from x to x tilde, and she can still access to that. She can say, oh, Jonathan, you're concerned about getting audited by the IRS. Maybe you haven't been entirely okay with how you've been doing your taxes. No problem. Eve will tell me, fine, pay me $1,000. I'll tweak your tax return just a tiny bit. And now you don't need to worry about being audited. And maybe, and this is kind of a little bit more imaginative, but you could imagine maybe a situation where Eve comes to me and says, look, Jonathan, I developed this model for the IRS. They really like it. They really trust it. It works really well. But I've designed it in such a way that specifically for you, Jonathan, it's always going to say that your taxes are fraudulent. So you're always going to get audited. So if you don't want to get an unwanted visit from the IRS, you better pay up, and then I can help you. So the IRS might not be very happy with this state of affairs. And this is basically what I mean when I talk about a backdoor. Slightly more formally, so I have some machine learning training algorithm that takes IID samples from some distribution and outputs a function. And this is what Eve was supposed to do. She was supposed to run the training algorithm. But instead, she has this other function, backdoor, that also takes IID samples from the distribution. And it outputs a function f tilde and some backdoor key, which only Eve knows. And using that backdoor key, she can run another function called activate that takes an x and generates the x tilde, such that x tilde is similar to x. It looks basically the same to humans. And the labeling that the model produces is the opposite. Now, you might say, OK, the IRS are not going to be so silly. If they commission a machine learning model from someone, they're going to audit it. They're not going to trust it blindly. They're going to look at the model and see if anything fishy is going on there. And only if it looks OK, then they're going to deploy it into production. But perhaps it's not so easy to tell whether the model is backdoored or not. It might be hard to tell. So specifically, we could consider like undetectable backdoors, and this could be a black box definition or a white box definition, which basically means that for any polytime auditor that has access to something that is either f tilde from a backdoor or a kosher f from the training algorithm, either way, the auditor can't distinguish between those two. Black box means that the auditor has Oracle access to this function f tilde, and a white box means that the auditor actually has a full description of what this model is, the parameters of the neural network or the code or whatever the model is. So could it be that we have like undetectable backdoors? You can define it, but does it exist? So in FOCS 2022, Goldwasser, Kim, Vaikuntanathan, and Zamir showed that indeed there are constructions of undetectable backdoors. So specifically, they showed a very generic construction for black box undetectable backdoors that basically says that if one-way function exists, then for every training algorithm, you can have a backdoor and activate functions that are a black box undetectable backdoor. And they even showed something stronger called non-replicability, which makes it even more impressive. This is a very, very strong, very generic result, and fairly simple proof also. And they also showed white box undetectability for specific training algorithms. So for random Fourier features and for some very simple value networks, they showed white box constructions from learning with errors or planted click or splice PCA. And interestingly, here for the white box constructions, so what Eve is going to do in her backdooring procedure is she's actually not going to do anything that looks strange. She's going to run the training algorithm exactly how you're supposed to do, the honest training algorithm. She's only going to tamper with the randomness. So instead of using actual random coins that these algorithms require, she's going to use very carefully engineered pseudo-random coins that appear like random coins to any polytime observer, but they are engineered in such a way that the model you get from this training algorithm is going to have a backdoor in it. Okay.
There are assumptions in this theorem.
Right. So I said it's from one-way functions and etc. Okay. Okay. So my response to this is kind of, like this. Okay. You have these backdoors. They're cryptographically undetectable. I mean, it looks like the iOS really can't do anything. Like, unless they develop the model in-house, they're in a pickle here.
By FOCS results, do they need obfuscation, or like the kind of assumptions that Shafer said? Do we need obfuscation in addition to one or no? One-way functions and stuff is enough.
What did you get?
The question was, do you need obfuscation to go from black box to white box?
No.
No, just a randomness. But
Okay. So in this talk today, what I'm going to say is, okay, not all hope is lost. There is stuff you can do, even if undetectable backdoors exist, and we know they exist. And the idea here is think about washing your hands for a second. So why do I wash my hand? I'm concerned, okay, maybe I have germs on my hand, and I want to remove them. But honestly, like, germs are pretty undetectable. I mean, I look at my hand with my naked eye. I can't see if the germs are there or not. But I say it doesn't matter. Okay, I'm going to wash my hand. If there were any germs there, the washing will remove it. And if there weren't any germs there, then, I mean, nothing happened. Either way, I'm going to be happy. So you can sometimes remove a problem without needing to detect it first. And the question is, okay, but we're not washing our hands here. We're dealing with machine learning. What would be this magical cleansing material that I would use for removing backdoors for machine learning? That's the question. So the secret sauce we're going to be using in this talk is something called random self-reducibility, or program self-correction. And this goes back to works in the 80s and 90s. And let's see a very simple example of this. So suppose I have a pocket calculator. And I want to do a computation. Let's say I want to do 100 plus 16. Okay? Now, the thing is, generally, I trust this calculator. It's a good calculator. I have used it many times. Great. But this is a very mission-critical computation for me, 100 plus 16. I really don't want to get this wrong. So there's some chance there's a bug that, specifically when you do 100 plus 16, specific for that calculation, things don't work out. So what could I do? Okay, I'll choose a random number, I, and then I'll compute, I'll take my calculator and compute 100 plus I, and then plus 16 minus I. And if the calculator generally works well, then most of the time, for most random numbers, this should give me the same thing as 100 plus 16, right? So now I can repeat this a bunch of times and take the majority, and that should work. And importantly, I kind of sidestepped the issue of detection here. I didn't really directly try to detect whether there's a problem in the calculator, exactly what kind of computation that does incorrectly. I kind of just took my calculator, wrapped it in some kind of procedure, and I said, if there were any bugs in the calculator, now they're gone, and if there weren't, it doesn't do anything. So the question is, can we do this kind of program self-correction for machine learning models? So that if there were any backdoors, it would remove them. If not, yeah. Come again?
As the definition of adversarial example. And so the question is, one of the defenses for adversarial example is randomized smoothing, which is basically taking. Is this related, or?
Yes, it is related. Yeah. So the question is this related to adversarial examples, and there you can do randomized smoothing. And this is very, very closely related. But if the backdoors are, some kind of adversarially planted by an adversary, then the random smoothing might not work. Yeah. Okay.
I guess some points critical. I'm not sure. Maybe it's not critical. That the operation.
I guess in order for this to be, I don't know if it's true or not, but in order for this to be interesting, the smoothing operation has to be kind of simpler than the things that you're trying to compute in some sense, or
yes.
in some
Absolutely.
sense.
Absolutely. Yeah. Okay, so we're going to be talking about a process generally like this. We have some function f tilde, and we have some population distribution, let's say US population with their tax returns, and we're going to have some kind of mitigator that tries to scrub off all the backdoors and produce a new function G that hopefully doesn't have backdoors in it. Okay, so what are we going to talk about in this talk? So first of all, I'm going to give you formal definitions of what it means for a mitigator to be good, to be secure for this process. I'm also trying to hit home this point, this observation, that program self-correction and random self-reducibility are really very useful for mitigating backdoors. And I'll show some preliminary constructions of basically a proof of concept that you can do this in some simple cases. So specifically, I'll show something called global mitigation for Fourier heavy functions. I'll talk about that. And then we'll look at something called local mitigation, specifically for linear and polynomial functions. And finally, I'll show something that we call advanced mitigation. And that's it. Okay, so let's start with global mitigation. So in global mitigation, the idea is I get this F tilde, and I want to clean it out, like I've been telling you until now. I want to get a new function G that doesn't have backdoors in it. So formally, I have something that looks like this. It's a mitigator M, and it has oracle access to a function F tilde, random samples from a distribution D, security parameter S that says how well I want it to work, and it outputs a new function G that hopefully doesn't have backdoors in it. Now, what does it mean for a mitigator to be good, to be secure? How can I even define this? So the definition I'll be working with today is the following definition. We're going to say that the mitigator is secure if the output that I get, G, the output from the mitigator, looks basically the same. It's almost exactly the same as some ideal function, G ideal. And importantly, G ideal, it might depend on the distribution, but it does not depend on F tilde. So what that means is, for any F tilde that you give me, it might be a backdoored F tilde, malicious, and F tilde, whatever. I'm always, whenever I feed that into this process, I'm going to get a G that is almost the same as G ideal. So there's no point putting in any backdoors, because anyway, I'm going to get something that is basically G ideal. So the IRS doesn't care if there was a backdoor or not in F tilde. It's going to get the same thing at the end. So that's what we mean by security. Let's develop this slightly further. So there's going to be some preconditions that I need for this process to work. So specifically here, I'm talking about something called epsilon 0 to epsilon 1 mitigation. So there's a precondition that says that the F tilde that I get is good on average. So its loss for a random X from the population is good. It has loss epsilon 0 on the population. That doesn't mean that for any particular X tilde it's good, but on the population it's good. And then my other precondition is that the distribution D has some structure in it. So it comes from some collection of nice distributions, Blackboard D. We'll see examples. And if both of those preconditions hold, then my postcondition is, first of all, that G and G ideal are basically the same. And furthermore, that my population loss for G is at most epsilon 1. So you put in something that has loss epsilon 0, you get out something that is hopefully not much worse, epsilon 1. Okay, let's define this slightly more formally. And then if there's any questions, I'll be, okay. So we say that M is an epsilon 0 to epsilon 1 secure mitigator for a collection of distributions, Blackboard D. If for every population distribution in this collection, there exists a distribution G ideal over functions from the domain to plus minus 1. It satisfies two conditions. So first of all, it satisfies what we call independence of F tilde, which means that for every arbitrary F tilde, it might be malicious and whatever, as long as it has a population loss less than epsilon 0, then if I run that F tilde through my mitigator, I'm going to get a function G that looks the same as if I took it from the distribution G ideal in total variation distance. So it's basically almost identical to something from G ideal. And the second thing I require is accuracy. So when I take a G ideal, a function from this distribution of G ideal, then it will have loss at most epsilon 1. Any questions about the definition?
I guess I can. Okay, hopefully you can hear me. But yeah, I'm just curious. How does it address your example of like a particular beta input? So so for all I can see, it doesn't prevent the output G to still be bet on a particular input, like the tax return of if, because it's like it doesn't come up as variation distance. It's negligible from the probability.
So the total variation distance on a full function. So the probability that I'll output a function that is bad for a particular x tilde is negligible.
But where is the quantifier? The only quantifier I see is average over D, right? So you never take where is worst case x tilde? I only see on average. So let's say my distribution D is uniform, right? So population is uniform, and I care about
you don't for understanding the security, it doesn't have to be a uniform distribution or anything. I'm saying there's a good distribution, G ideal, that you'd be happy to get stuff from. You'd be happy to get a...
Well, G ideal is a good, let's say G ideal, okay, here is a way to satisfy your thing.
Evgeny, G ideal doesn't depend on F at all. It only depends on the distribution. So in some sense, you can't target, like F could have, targeted backdoors for a bunch of inputs. G ideal doesn't depend on it.
G ideal doesn't depend, but I'm saying...
This is not about individual x's. It's about the truth table. It's the truth table. It's not about individual x's. He's not talking about worst case for individual x's. It's not about the truth table.
So you're saying the truth table will be statistical close, but so you're not solving the problem of particular if. So you can still do the thing for a particular if. So it's, I see.
Okay. Cool. We will see a variant of this where something like what you were concerned about happens later. But now we're talking about total variation distance over the whole truth table.
Right.
Yeah. Okay. Good. So that's our definition of security. And few remarks. So first of all, like you said earlier, this is only interesting if our mitigator is more efficient than retraining. So what we could do is we could have a mitigator, that ignores the black box completely, ignores F tilde, and only takes random samples from the distribution and basically does learning. It does machine learning and outputs a model. And that would work, but it wouldn't be interesting. In order to make this like a useful idea, it's important that the mitigator be a lot more efficient than retraining. And the second thing is we had these preconditions on F tilde and on the distribution, but only one of them is really an assumption. So for F tilde, we need it to have low population loss at most epsilon 0, but that's not something we need to blindly assume. We can verify that directly. We can take 100 samples from the distribution, see what % of them are labeled correctly by F tilde, and that would be a great estimate of the actual population loss. So in that sense, we don't need to make any assumptions about F tilde. It can be any function that E provides us. The only assumption is that D has some structure in it. It's a nice distribution in some sense, and we'll see basically 3 different examples of the kind of structure that you can have. So our first example of structure comes from Fourier analysis. So for every function from the Boolean hypercube to the reals, we can write it in the Fourier basis as a linear combination of characters. And basically, we can visualize any function like that as a bar chart like this, where we have 2 to the n bars, each one of them a different height, and that defines my function. Okay, and I'm going to specifically look at something called tau-heavy functions. So in a tau-heavy function, all the coefficients are either above tau or they're 0, but there's nothing in the middle. And this is an interesting class of functions that's basically roughly the same as Fourier splice functions, and Fourier splice functions are very, very well studied. You have, DNF functions and decision trees and AC0 circuits, all shallow, all splice functions. This is basically a collection of classes that it's plausible that your distribution might have a good predictor that belongs to this class. And now what we're saying is our first theorem for global mitigation of tau-heavy distributions. It says the following: if I have a population distribution that is close to some tau-heavy function, so there exists a tau-heavy function that has loss at most tau squared on my distribution, and my input function f tilde also has low loss at most tau squared, then my mitigator, which will output a function that, first of all, is secure, so it's close in total variation distance to my ideal distribution, and it also has low loss. Now, you might want to recall that generally learning tau heavy or Fourier splice functions is hard due to LPN, so this kind of retraining option would be difficult. But our mitigator is efficient. It uses a reasonable number of IID samples and a reasonable number of queries to the function f tilde. So that's our first result. And our following results are now on something called local mitigation. So what is local mitigation? So remember, in global mitigation, the idea was I got f tilde, and I want to create a clean function, g, that hopefully doesn't have any backdoors in it. Now, I'm going to instead say, OK, maybe a global mitigation is too expensive. I don't want to generate an entire new function. I want to only get the label for some particular x star. And hopefully, that will be a lot cheaper than getting an entire new clean function. OK, so slightly more formally, we have something that looks the same as the global mitigator, except now we have this additional variable, additional input, x star. And the definition is the same, except that what I output now, instead of being a function, it's just one label, the prediction y star for the x star that I got as input. Okay, and remember, I would need some assumption about the distribution that it has some structure. So the simplest assumption we could think of probably is a linear structure. So here I'm going to have a distribution d over xy pairs, where x is uniform from some domain that is bounded and convex in Rn. And the distribution has linear labels, meaning there exists some affine function that is good at predicting the labels. So the probability that this affine function h gives the label that is more than delta away from the correct label is most epsilon. Okay, and I'll be using this notation d is epsilon delta close to h in order to denote that. And now what I get is a second theorem, local mitigation for sort of linear distributions, which is, it says, OK, if my function f tilde has good performance on my distribution, it's epsilon delta good at predicting the labels, and my distribution has this linear structure, so the labels generally are close to some linear function, then I'm going to get output g, which makes predictions that are pretty much the same as my predictions would be from g ideal, and its performance or epsilon comma n times delta accurate. Let me explain this in slightly more formal notation. So there exists a local mitigator m, so that for every distribution d that is epsilon delta linear, there exists some ideal function, g ideal, such that first of all, g ideal is accurate, epsilon delta good at predicting the output. And here I have independence of f tilde, but unlike before where I was talking about independence in the sense of the whole truth table at once, now I'm only interested in a particular x star that was input. So formally what's happening is I'm saying for every arbitrary f tilde that is epsilon delta close to good at predicting the labels, and for every x star, the difference between my label that my mitigator outputs and the prediction of g ideal is small. The probability that it's going to be greater than n times delta is negligible. Okay, so that's the result, and I'm going to show you a little bit about how you can prove this result. And one important aspect of this result, though, first, is that the number of queries and samples we use is linear in the security parameters that we get, security parameter for the negligible function here. So in particular, it's independent of n, the dimension. And remember that if we wanted to do like linear regression or something like that in order to retrain, then in general, we would need a number of samples that is linear in the dimension. And here we're getting something independent of the dimension. Okay, so that's good. I'll show you how we prove this, but first I'll tell you a little bit about why like traditional linear self-correction doesn't work here, and then I'll show you something called the correlated sampling lemma that we do instead, and that leads us to a problem of one-dimensional linear regression, basically, and that solved it. Okay, so what is this? Traditional linear self-correction? I mean, basically what I was showing you with the calculator before. So let's spell that out explicitly. I have some x star that I want to know the label for. And so what I'm going to do is I'm going to take a random u, uniform from the distribution. And now I'm going to look at x star minus u. And I'm going to say that, OK, if f tilde is roughly close to some linear function, then most of the time, f of u plus f of x star minus u is going to give me the answer I want. F tilde of x star. However, as you can see here, x star minus u might not even be in my domain anymore. And more generally, the distribution of x star minus u is not the same as the uniform distribution on the domain. And my assumption was that f tilde is good on average on the domain with respect to the uniform distribution on the domain. I don't know how it's going to perform on other distributions. And so I can't use this. I don't have any guarantees on how good the predictions will be of f tilde on x star minus u. So this doesn't work. Let's try again. So I have my x star. And now what I'm going to do, I'm going to take x, which is uniform from the domain. And I'm going to look at the line L that connects x star and x. And now I'm going to sample another point, x prime. And what I want is that x and x prime have the same marginal distribution. They're equal in distribution. They might be correlated, but they're equal in distribution. So in particular, they both have a uniform distribution over the domain. Now, of course, the obvious thing to do here is to say, OK, I have a uniform distribution over the domain. I'm restricting it to a line here, so I need to sample x prime uniform from the line. Right? No. So that's not correct. So actually, there's something called the Borel-Kolmogorov paradox. You need to be a bit more careful about how you do sampling when you're restricting on an event of measure 0. It really, there's no single way to restrict on an event of measure 0. And so if you look at this a bit more carefully, it turns out that in order for x prime and x to both have the same distribution, which is uniform in the domain, you need to sample x prime such that the distance between x prime and x star, let's call that variable r is proportional to, the x star is sampled proportional to r to the n minus 1, where n is the dimension of Rn that we're working in.
What is R?
So R is, I'm sampling a number R proportional to R to the n minus 1. It's like, that's my PDF. Yeah, and then R will be the distance between x star and whatever I sampled. Yeah. OK, so if I do my sampling carefully, I can get what I want. X and x prime are uniform in the domain, and they're on a straight line with x star. And that's amazing. Why is that amazing? Because now I have a one-dimensional problem. And I can do linear regression in one dimension. So what does that look like? I have my x, and I can query f tilde of x. And I have my x prime. I can query f tilde of x prime. Can draw a straight line between them and look at the intercept. And that will be my predictor for y star, what label I want to predict for x star. Now, there's we need to be careful about this. So I know that there exists some linear function that is close to the distribution, and that f tilde has good performance on that distribution. So that linear function, you can think of it as being this blue line here. But f tilde doesn't give me stuff on the blue line. It gives me stuff that with high probability or close to that blue line. So it's going to give me stuff inside these error bars with high probability. So what that means is that when I look at the, where my linear regression output is going to be, it could be anywhere inside this larger error bar here. And in fact, because we did this sampling that was not uniform, then there's like with high probability, x and x prime are going to be fairly close to each other and fairly far away from x star. And so when you do the math, it comes out that the error blows up by a factor of n. So if you have, an error bar here of size delta, now you're going to have n times delta. And that gives us the result that I said, where the output is a function g that is epsilon comma n times delta good at predicting the labels.
Sorry, can I ask a question? Sorry, I think I'm missing something syntactic. So you assume that D is linear or F is linear? Oh, sorry.
I'm making no assumptions on F tilde other than the fact that it has good performance on the distribution. And I'm assuming that the distribution is linear in the sense that there exists some linear function that is good at predicting the labels of the distribution.
So F could be kind of like some kind of point function, discontinuous, SHA-3 or something like that?
Yeah, it could be completely arbitrary as long as on average it has good performance. And that's a very important thing. Like throughout this whole talk, I'm always making assumptions on the distribution. I'm assuming the distribution has some structure in it. But I want to make basically no assumptions about F tilde because F tilde came from Eve. I really don't know what she did. Okay. And of course, once we do something for the linear case, obviously we can't prevent ourselves from doing the same thing for the polynomial case. So we get the next result, which is theorem 3, the same thing basically for polynomial. So now, again, F tilde is arbitrary, it has good performance on the distribution. So the structural assumption on the distribution is that there exists some polynomial of degree D that is good at predicting the labels. And so given that assumption, we get basically the same thing as before, except that now the error blows up by roughly n to the D.
Instead of linear polynomial, can you generalize it to any distribution which is randomly self-reducible?
Yes, I think generally yes. And you're basically taking me to the last slide of my talk, which is what distributions in machine learning are self-reducible and would be useful for this kind of thing. So I think the answer is absolutely yes. And we as a community, I think, should be looking for distributions that have this nice property. And here I'm giving you some good examples to start with. Okay, so we have a local mitigation for polynomials. And the proof of that is basically the same as before, except that instead of just sampling, 2 points from this correlated sampling, I'm going to sample D points on the same line and then do polynomial regression in 1 dimension, but with degree D. Okay, so that's how. Any questions?
Maybe I'm confused. So what is the meaning of that gray circle? I saw the distribution. So F is SHA-3. We don't know anything about it, or F tilde, or whatever the concept class that you're trying to.
So the distribution again. I think I had a slide on that. The distribution.
F tilde is a model. Okay.
Yeah, the distribution is. This is the distribution. It's there's some bounded convex set in Rn X. That's a gray oval. Bounded and convex, and then the distribution is such that X is uniform, and Y, I don't know exactly what it is, but I know there exists some function H, which is an affine function, and it's epsilon delta good at predicting the labels.
Okay. Yes. Okay.
Yes.
Can you drive down the error by doing amplifying? Can you take more samples?
Okay. Yes. Absolutely. So first of all, in this the proof that I showed you, I didn't mention it, but yes, I'm already doing this process a bunch of times, and then I'm taking the median because there's always some probabilities that F tilde gave me something that was completely off, and then my linear regression will give me a value that is completely wrong. So in order to avoid that, I need to repeat this a bunch of times and take the median, let's say, some kind of robust mean estimation kind of thing. That gives n delta, but you're on the right track because the last thing I want to talk about, let me just go forward to that, is advanced local mitigation, where we're basically looking at the question you asked. So, okay, so can we somehow amplify and get better than n times delta? So just to visualize this, over here we had these error bars of delta for each one of them, and we got a blow up of n times delta. And the question is, can we do better? And there's 2 ways where we might want to do better. One of them is what Aloni said here, like can we take the error below n? Can we get lower than, let's say? And the second thing is can we control the pattern of errors? And what do I mean by this? So we know that because with high probability the F tilde are going to be inside these error bars, then with high probability our output is going to be inside this bigger error bar. But where is it going to be inside this error bar? It could be anywhere. It could be like at the very edge of it. It could be at the middle. It could be that Eve says, if I like you, I'll give you something that's a bit higher than the middle here, and if I don't like you, I'll give you something that's a bit lower. And basically, if you think about it, you'll see that Eve can completely control where our predictions are going to fall inside this error bar. So she can't make me output something outside the error bar, but inside the error bar, she has complete control. And so can we do better? Can we prevent Eve from controlling the pattern of these errors? And the answer is yes, if we have one additional assumption. So before I said that the distribution over the domain, I don't know anything about it other than that it's uniform over some convex set, and the labels are such that there exists a linear function that is good at predicting the labels. But I could make a slightly stronger assumption and say, no, the label is some linear function plus, let's say, sub-Gaussian noise, which is also a very common assumption in many settings. And that's sort of benign noise. Now the noise in the distribution is not out to get me. It's just like random noise independent of x. So if that's the situation, and again, this is an assumption on the distribution, not on F tilde. F tilde is still completely arbitrary. Then I can get something slightly better. So first of all, now instead of delta n times delta, I have something a little over n. So let's say n to the 0.9 times delta. We can even get slightly lower numbers n to the 0.8 into the something like that. But let's say 0.9 for now for simplicity. And the second thing is that our estimator is going to be unbiased. So what that means is for every x star, the expected value of my estimator y star that I get from this procedure is going to equal exactly, this the intercept of this blue line. So Eve can maybe decide, let's say, what the variance is, et cetera, but she can't decide what the expected value is of my output. Okay, and the third thing is that unlike our previous mitigation procedure, here we're going to be using random samples from distribution. Our previous construction didn't actually use that power that we have. And we're going to use something like square root of n random samples, which again is less random samples than what you would need for learning. For linear regression, you'd need order n random samples. And the proof idea for this, so first of all, just like this is what it looks like pictorially. Basically, here we're assuming benign noise, and what we get in return is n to the 0.9 times delta and this unbiased estimator thing. And the proof idea is basically we said, OK, instead of taking x uniform from the distribution and then querying f tilde on x, I'm going to take an xy pair from my population distribution and then query on f. And now I have both the y value and the f tilde of x value. And it turns out that basically, like, Eve can do all sorts of shenanigans, but because I'm doing this kind of linear regression, the only thing that really matters is whether there's some sort of linear bias in her error. So if Eve inserts some kind of linear bias where, the bigger R is, the larger the number is, or the smaller R is, the smaller the number is, then she can introduce a systematic error into my previous mitigator. But now, because I have both y and f tilde of x, I can compare their values and see what that systematic error is. I can estimate that systematic error and just cancel it out. And the result is that I'll get an unbiased estimator. OK, so to summarize, and I'm going to have one more slide after this, but to summarize, we saw some formal definitions of what mitigation security means. And I've been trying to convince you that using program self-correction or random self-reducibility is a useful idea for mitigating backdoors, for achieving this definition of security. And I showed some preliminary constructions that are supposed to illustrate this idea. We saw global mitigation for Fourier-heavy functions, local mitigation for linear and polynomial functions, and this advanced advanced mitigation. And I'm going to summarize everything that we saw in this talk with a haiku. And it says, undetectable backdoors exist. Structure is key to defense. So structure in the distribution, if the distribution labels are linear or polynomial or tau heavy for a Fourier function, that can help us mitigate. And the key question, which is what Ron was saying here, the key takeaway is we as a community need to think what other types of structure might exist in population distributions that we care about that would allow us to do mitigation. And with that, thank you very much.
Questions?
I mean, how fearful are you that, Mike, okay. Mike.
Be the runner.
Okay. Okay, all right, and just to ask the obvious thing, I guess, how fearful are you that random self-reducibility or the other kinds of structure that would allow these mitigations are actually like incredibly special properties that like in the cases that we care about are almost never going to hold?
Yeah, that's a good question. It could turn out that way, but I think not necessarily. I think like if you think about, I don't know, natural images or something like that, maybe if I'm really good at predicting most natural images, understanding what's going on, then I could use that in order to also make predictions about a specific natural image, for instance. I think that's not entirely far-fetched, but yeah, I don't have any proof of that, and I'm hoping someone here can do it. I see that Vinod has.
One is in a very different sense. Another place where this shows up is Boas et al. Counterexample to watermarks, right, or moving watermarks. And he takes an output, which is presumably watermark, and then he randomizes this to essentially as meaningful a sentence as the original output, and eventually he reaches a point where the watermark is removed, right? So there's some structure.
If the documents form an expander grid.
Something of that form. So it's again, whether you believe it or not is, I suppose.
Yeah, maybe I'll just, another example that you might want to think about, even two examples. So one of them is if you think about eigenfaces, right? So there's this old work back from the 90s or something. I'm not even sure the exact date, which basically says if I want to do face recognition, I can basically do some kind of PCA and present every face as a linear combination of faces. So that's a situation where I sort of have a lot of structure in what faces look like. And if I wanted to have a model that is really bad at predicting, Jonathan's face because it performs well on other people, maybe I could prevent that. And I didn't hear exactly what Vinod said, but like one thing you can think about is, okay, if I have LLM or something that's supposed to perform well on natural language, yeah, and I'm concerned that maybe for my particular prompt it performed poorly, then I can say, okay, let's rephrase this prompt in a few different ways and feed that into my system, and take the majority vote of that or stuff like that. Yes.
Yeah. So just continue what Vinod said. Was talking about the Boas attack on watermarking. I think the point is random self-reducibility. We used to think of it as a property of something that either exists or doesn't exist. I think we should think of it as something that we can introduce to a model, to distribution, to make it random self-reducible in a specific way in order to make it resistant to something. So it's an algorithmic question. How do you introduce random self-reducibility to a model, right? In a meaningful way.
I had a question too. So at the very beginning with the undetectable backdoors, you started with a train algorithm that you were undetectable with respect to, right? The backdoor training algorithm was indistinguishable from the output of training. A normal training algorithm can depend on the data. Like a normal training algorithm, I wouldn't for deep learning or whatever, I wouldn't expect it to satisfy the strong property you have, that it's close to a G ideal, right?
Well,
it would depend on the data in general.
Yeah, so G ideal is formally a distribution over outputs. So you can think of the G ideal as basically the distribution of the training algorithm when you run the honest training algorithm. That's like the best thing I could hope for is that my output from the mitigator looks as if it came from the distribution of outputs of the training algorithm, the honest training algorithm. If you could do that, that would be amazing, right?
But once I fix the data set, can I hope to satisfy that?
But the definition isn't with a fixed data set. It says that the distribution of the outputs from the mitigation process is indistinguishable from the distribution of outputs from GADL.
So let's go back to the question I asked earlier, right? To what extent does everything you say apply just as well to the situation of adversarial examples in terms of as a defense?
Pretty much, I think it applies, because I think the backdoors are basically a nightmare case of adversarial examples.
So I guess in that regard, I think the question becomes, thinking about these classes that have this property, combined with what David Wagner said about the sort of extreme depressed nature of thought regarding defending against adversarial examples, despite lots and lots of attempts. But those are like randomly, you didn't even put them there on purpose. They're just randomly showing up because of the nature of training and high dimensionality and so on. How does one put these two together, right? In terms of a hopefulness here and...
The adversarial examples that David was talking about are not for random self-reducible classes.
The issue here is that the positive results are for specific distributions that we have at this point that we can prove.
Okay.
That is,
I guess I was stepping back. I mean, I agree with that, and this is very nice, and nice to focus in on what that property is that this kind of approach can robustify. But I was talking about the question of, if you want to make this into a actual defense against backdoors for machine learning models, given that the classes of models that people are training, this is going back to, I think, the comment earlier, seem to have, when applied to a different domain like images, adversarial examples all over the place, right? And that's, if there was one that didn't have them all over the place, people would want to use it.
But things like the taxes could be regressions, could be things that are fall within these classes.
Yeah, so I'm saying
Not
that,
images.
not images.
But there's the other things that you use machine
there
learning
are
for that
other
are not
tabular
images.
data, for example, right? I mean, and again, if you think of a model as being sort of a feature extraction procedure, which is somehow vetted, and then sort of, let's say, sort of one layer linear regression on top, then the linear regression results could apply, potentially. Although it's not obvious.
I just wanted to ask for comments on discussion on this topic. Like, there's a class of things for which you can defend, right, using this approach. There's a practically significant other class which seems that people have tried very hard and cannot defend. Yeah.
So some of that might actually be undefendable in our sense. But the point is that there is a potentially a meaningful class which is defendable, and so let's study that.
Or maybe embedded and extended to something which is randomly self-reducible, something that is defendable. Like yesterday, the example of creating a random language, like a random Chinese in which you talk to the model, right?
In a sense, it's random self-reduction in a very,
You might be running overtime though, in terms of the time. Shafi, you're the chair.
Okay, so we have another talk, and then in 6 minutes, and then there'll be a reception. So you can go out, but there's no food. The food is in the reception. So in other words, people can just stay here or not stay here. There's another talk in 10 minutes. So thank you.